Calculus 3, class number 9, part 1. We're going to look into graphs and level curves, and first we are going to define a function. So as there is a definition for single variable function, there is a definition for multivariable function as well, which goes exactly the same way, except now instead of a single point input, we are going to have a 2D or a 3D or a 5D or whatever D, so multivariable input. Something like this could be on one of the exams to state, maybe exam 2, maybe final. And it goes like this. Function is a rule which assigns to each ordered pair xy in the domain a unique z in the range. So clearly this is geared towards the 3D case because we have two-dimension input and then one-dimension output. Put them together, it's a 3D xyz. The notation for something like this would be the z equals f of xy. So the same like the notation earlier, except you have an extra y in it in the domain. And then we also have the implicit form. So this would be explicit form. You will not always be able to separate z equals everything else. Just like you were not always able to separate y equals everything else, right? You had a circle, x squared plus y squared equals z squared equals r squared. It is not a function, but still we can do stuff with it, right? So the same thing is going to happen here. It might not be a function, but we'll still be able to do things. So explicit form would be f of x, y, z equal to 0. So implicit form. So what are the quick examples? The quick examples would be, let's say, z equals x squared cosine y. So that would be an example of a function. And let's say, so that would be explicit, because we are able to write z equals everything else. And let's go with the implicit form. Let's say 3x y plus 2x z squared minus cosine z equals to, I don't know, 2, whatever, implicit. We're not going to do anything with it, just put the stuff on a pile, it really doesn't matter. So if you take a look at the second equation, we cannot separate z out of everything, so that's it. It's implicit. So now what do we have? To graphically represent this, to some extent, we have xy, which is domain. There's a set of all values from where the point xy will map onto a single point z on the z-axis, which is range. So it will take two values for us to map into a single value. What does that mean? Well, here we go. Z equals 2xy squared, domain 0.32. So f of 32, which is that z, is going to be 2 times 3 times 2 squared, which is what? 4,824. So this is what we have. In order for us to understand, so function is a rule, domain, range, and the word unique, underlined twice. This is the standard setup. We had this also in pre-calculus 1. We had this in calculus 1. Same definition. Rule points towards in which way x and y combine in our equation, whether it's through trig or through logs or through multiplication. So whatever way they combine together, that's the word rule. There's some kind of equation that connects them. Domain, I already said, it's the set of all values that we are allowed to use as input. So we have to be a little bit careful. What are the values that we can and cannot use? The word range is the set of all output values. We saw that the one-dimensional output is just a number line. Could be from negative infinity to positive infinity. Could be less than that. And the most important, things don't work. Or maybe too many people. The most important word unique. That's the one that makes function. The word unique is the one which creates the rule to be a function. Without the uniqueness, you end up with relation. A relation can be anything. You can have two people, let's say, finish the race at the same time. Or if there are no overtimes, two teams score the same team and it's tied, right? So the same score and then it's tied. None of those would be functions because the input, right, different inputs produce the same output. The same input cannot produce two different outputs. That's what I want to say. Same input cannot produce two different output values. That breaks uniqueness, and because it breaks uniqueness, it is not a function immediately. It's not a function. That would be like you trying to be at two places at the same time, right? Since you're not electrons, you can't do that. Yeah, quantum world is weird. We'll discuss in the next class. QED. No? We'll do more Calc 3 then. What else? So now we would like to know how to find the domain. What's the domain? Domain is set of all inputs. Good draw. Set of all inputs, right? So, set of all inputs. Looking at the equation, we should be able to determine what are the values for x and y that we cannot use. Sometimes we are able to block off the region. Sometimes we can eliminate half of the plane. The input is the xy plane. It has infinitely many points, not just on axes, but everywhere else. 0.11 could be input, but it might be banned depending on what kind of function you have. So let's take a look at a few examples, and it's really up to how creative you get to analyze the cases and how much math you know from the previous courses in terms of domain and range. So let's take a look. Z equals ln x minus y. So what is the domain? Is it all real numbers for both x and y, or there is some kind of restriction? So we always have to start first by looking into what the 2D case ln did. You know, y equal ln x. We can graph that one. We see that the original domain was all x's larger than 0. 0 would produce negative infinity, and negative numbers were banned. Complex values can bring those in. Those of you who came to my lectures last semester, you know those independent thingies. You know what we can do with complex values there. Now, what's happening with the function ln x minus y? Well, we see that this parenthesis, the argument of ln, has to be larger than 0 at all times. So, there we go. What is in domain? Any point that satisfies this condition is automatically in the domain of ln x minus y. Now, obviously, you can massage this into an equation for the xy plane, and then you can graph that, and you will have a visual representation of the region that will give you the points that you can plug in and the region with the points that you cannot plug in. So this one over here can be solved as x larger than y, so y less than x. We can graph domain. In this case, up has to be a dashed line. Has to be a dashed line because the line is not included. If you are graphing inequalities, without equal sign is dashed, with equal sign is solid, which means that the line is the part of the solution set. In this case, dashed line, so x and a y. And where are the y's less than x? Right? Below the line. Or as my algebra students would say, you get to shade US. Because it's US and Canada border. The line. So any point over here when y is less than x. Now you can test this, right? If you pick this point here, it's 1, negative 1. When you plug that in, you get ln of 2. That's green, right? If you pick this point here, you get negative 1, 1. And you plug that in, you get negative 2. ln of negative 2, that's going to be the complex value answer. So we cannot use that. All right, you try one. Okay, so the argument under the square root can also be equal to 0, right? For ln, you're not allowed, but for square root, yes, you are. So 3x minus y greater or equal than 0 is where we start. Move y to the other side is 3x larger or equal than y. So what we need to graph is y less equal than 3x. For visual representation. And this time we use solid line. And we shade the region where we have all of the points. So that's the story about the domain. Actually, let's do one more. See what you guys are going to come up with. I'm interested in what you're going to come up with this. Let's see, seatboard. What do you got? This is the high school. This is a high school problem. No, it's an unrelated problem. Hey. I know. You want to get into electrical engineering or something with engineering, where we come from, we got to know how to put this. This is coming out of high school. If you don't know this, then don't worry about anything else. Such is life. So I'll leave you to meditate on this until the end of the class, and then 10:15 we reveal the answer. But we want to talk about this now. Look at the beautiful equation over here. No ln's. Hey. No cosines. She's testing this problem to the whole world now. It's like, well, that's not what we learn. No? What happened? Pet the dogs? Have you? I mean, it's okay if they eat twice. They don't eat at all. What'd you feed dogs? A cat? All the cat people go like, no. You should. 1, 2, 3, 4. Yeah. This is fine. That was a solid 4. Ready? 1, 2, 3, 4, 5. 5 and 3. Anyone, please. Anyone. Answer. Z. What happened? Okay. So what is that? It's a circle. So, but actually what circle? Is it a circumference or everything inside, right?
So everything inside
yes.
domain.
And the circumference.
And then the line.
The line, circumference. So, since this is a square root, we are going to say 4 minus x squared minus y squared less equal than, sorry, greater or equal than 0. Then we move x squared, y squared on the other side. And then if we write it like this with my awesome drawing skills, we have domain to be everything inside, including the circumference, which is why it is not dashed. Now I'm going to ask you, because you should know, what is the shape, the Z shape? What is it? Half a sphere. Top half of the sphere. Because you see there should be a plus minus in front of the square root if you want both halves of the sphere. You only have a positive half of the sphere in this case because it's plus, so it's the top portion. And the bottom portion that is below xy plane, because this sphere is centered at 0 at the origin, then we have the bottom portion is not there, so this is just a half a sphere. Now, as you're imagining the half a sphere, best we can do. So half a sphere, you have the circle on the bottom, right? The equator, all right? Observe that anywhere inside the circle, right? Anywhere inside the circle, the points inside the circle will spawn these points when computed in the equation, will spawn z's, which give the shape of the object. All right? So circle on the bottom is the most that extends, and that's the domain. And think of that circle as the equator, right, on the Earth. And then the plane that cuts through the half of the sphere is the xy, which is the domain. And on that, you have all of the points. The point 1, 0 is clearly on the x, or point 1, 1. So point 1, 1 will give rise to, let's say, this point here. When you plug in 1 and 1, you get 4 minus 1 minus 1, so the z value of that point is 2. No, it's not 2. There it is. So 1, 1 gives us that. 0, 0 will be 4 minus 0 minus 0, then square root of that. Oh, it's the square root of 2, actually, the first one. 1, 1 gives us square root of 2. There you go. Magic. I used to play with kids. All right. There's going to be a lot more of that because I need shape. Good. We understand, hopefully we understand the domain. So domain will be the set of points on xy plane, set of all x comma y ordered pairs, which when computed in the equation that is given to us produces z value, and a z value paints the shape, right? Makes the shape. The next thing we're going to talk about are level curves. Level curves are lines that appear on the object when you cut the object with z equal a number plane. So, The best way to understand it is just take a look at the graphic. It is extremely easy to compute. We'll do that obviously, but let's understand. Level curves. So you have some kind of shape. That's the shape. Imagine the pile of sand, right? And now you cut that pile of sand with the plane that is perpendicular to the xy plane, which is your domain plane. So those planes, all that are parallel to xy plane, they're all z equals something. Z equals 1, z equals 2, z equals 3, z equals 4, and so on. So, as you are cutting this shape, you cut the shape here, and then whatever curve you get when you cut, you project that onto xy. Drop it down. So all of these lines are on xy plane, but we obtain them by cutting at different heights during where you look at the 3D object. So now these curves over here, the green curves, show, they're called level curves, and they show how the object progresses as you cut. So you see the wide circle, that's going to be wide around. Then you go higher, and then higher, and then higher, and then if you cut to the top, it's just going to be a little point. So when you look at this, you know what the shape of this one is. Now, if the shape does crazy things, then you have to label, you know, Z0, Z1, Z2, Z3, and so on. And if you see that they're not in order, that means that the shape went like that. So, who's very good with this? Well, obviously, military, and anyone who has to read the maps, because this is what we use to understand the topology of the terrain. So, if you look at the map over there, if you ever looked at the map, you saw a lot of these lines that are curved, going crazy. Well, those lines are all level curves. Whenever they are far apart, that means that the ground is flat or very slanted. And whenever they are very close together, that means that it's very steep. So when you are reading a map like this, and you are off-road driving, like military does all the time, right? You need to read this and find the path where these lines are far apart, because you don't want your trucks and things going on slopes like that, right? You have to find the path. So you take a marker and you try to kind of go through wherever they are, you know, far apart. If they get close together, that means that it's very steep. When they are far apart, not too much increase in height, because remember, level curves cut, and then technically the closer the level curves are, the higher the slope. Here's another another example. What you have here is a very simple shape, which is that. That's all you have, right? But it's slanted like this. And then as you cut with level curves, you see that you see parabola, parabola, parabola. So that's the shape you have, looks like this. And as you cut with level curves, you get this. What's the computation here? Computation is very simple. Equation is going to be given to you, z equals something, then you keep replacing z equals 0, z equals 1, z equals 2, z equals 3, z equals 4, and every time you put in one of these numbers for z, you draw a graph. You draw a graph for each one of them, and that's what the level curves are. Someone in your neighborhood didn't want to draw the graph, that's why I looked that way, don't worry about it. Another example, Another example, here's the wavy surface. And another one. Ah, the termite. Do you all see how these level curves relate to the shape? So usually on the exam 2, maybe on a final, I put in one of those multiple choice questions when I give you 4 shapes to choose, and you match the shape. I'm not sure if this book has problems like that. Yeah, they do. Perfect. So unfortunately it's not formatted well. So problem 38, matching level curves with surfaces. So you have 6, they give you the 4 brown ones, and then another 2 on top, that's 6, and they give you 6 level curves to match them, which one goes with which. So that will be a good practice for you guys to do. So for level curves, I mean, there's really no definition or anything, it's just a procedure. Compute z equals f of xy for z equals 0, 1, 2, 3, 4, and so on. Graph each on the same xy plane, and you have your level curves. So if you have half a sphere, what you're going to get are circles for level curves. So all you need to do is to compute for z equals 0, z equals 1, z equals 2. I'm just computing one real quick. So x squared plus y squared equals to 3. Z equals to 2. 2 equals to, oh wait, you square both sides, it's 4. And this is a point, so I only got 3. So you can do in between a half, 3 halves, and so on to get the other values. And that takes care of 12.2. After the break, 12.3.